Okay, so this is the first lecture of the structural dynamics class, and you found in the emails that I put on Blackboard, or the notes that I put on Blackboard, you know, information regarding the syllabus and so on, and when we will meet for the first time. Now, I have placed here on the left side of the board, I did my best so that this would be readable to you. I put here on the left side of the board certain list of words, if you'd like, which are simply intended to give me a guidance so I remember what the order of what I am supposed to be talking about. So this first lecture is primarily introductory, and let's begin with no further comments. My first word here is dynamics. So the course is called Structural Dynamics. Now, of course, we kind of know what structures are and so on. Well, what is it that we mean by saying that a problem is a dynamical problem, or a problem that belongs to the realm of structural dynamics? At this point in your career, we've all been, you know, we're all familiar with structural analysis, and what we mean by dynamics essentially simply is that when we have the structure under some excitation, we cannot neglect the effect of inertia. I mean, there is a slight twist that you could add to that, because it could be in other cases that you could also say you cannot neglect the effect of damping forces, perhaps. But that's kind of a, you know, maybe an unnecessary subtlety. The point here is that as loads are applied to a structure, the structure deforms. If at any time we can analyze a stress field that the loads are producing, and we don't have to worry about what is the inertia, then we just have a static problem. Now, if you want to be really literal, you could say that all problems are dynamic, in the sense that, that there is no such thing as a static load, because if the load was at some point 0, and then it became a value, then the load had to grow over time, right? So it was time dependent. Now, look, for example, at this case. Let's just to make this point, I won't dwell with it anymore because it's rather obvious. So let's say that we have this spring, right, with a constant K. Now, if I apply a load, let's say that we call the elongation of the spring, I don't know, y, right? And we apply a load at the end of the spring here, P, which is a function of time. Now, is this a dynamic problem? No, it's not a dynamic problem, because I can say that the equation of equilibrium of this thing simply says that the deformation y, right, of this spring is the value of the load divided by the spring constant. So there is no differential equation here, there is no dynamics. The response as a function of time is just the load as a function of time, right? And even though this could be whatever, we still have the same as a static problem. If this load was static, we would simply say that y is equal to p over k, right? So what made the problem dynamic, what makes the problem dynamic is not necessarily that the load is a function of time, but that the response of the structure to the load as a function of time is going to involve significant inertia response, okay? So this is just a static problem. Now, let's see, I'm going to try to keep the board sort of as clean and as visible as possible. So if we take that out and we say, well, what if we look at the same thing? Of course, the previous problem, or this spring, is what we call an idealized spring, right? Because even without thinking about it, I already assume that this is a spring with no mass, which of course doesn't exist. How can you build a spring and have no mass? But in our idealized mathematical sense, we say the mass is small enough for our purposes and so on. So anyway, it's just K. Now let's say that we attach at the end of the spring a mass having the value M, let's say. And in order to make it look reasonable, so it doesn't look like the mass is falling down, I'm just going to put a little bit of a roller there, and do the same thing. Apply a load P as a function of time and call the movement of this mass y, okay? Which is also going to be a function of time. Now, if we look at this and we isolate the free body diagram of this mass, right? Then we have the load P as a function of time. We also see that the spring is going to be pulling back as K times Y as a function of time, right? But, and we're only looking at equilibrium in the horizontal, right? In the vertical, it's obviously just the weight being carried. But if we look at that, that's not complete, right? Because this mass in general is accelerating, and according to Newton's law, right, we know that force equals mass times acceleration. Now, in mechanical engineering, it's typical to write things, you know, like that. Let's say force equals mass times acceleration. That means, I'm sorry, what did I do here? Where's the eraser? Not force times acceleration. The summation of the forces is equal to the mass times acceleration. That's what I meant to write. So this is Newton's law, right? The summation of the forces is equal to the mass times acceleration. In civil engineering, because we come from a tradition of statical structures and statical things, and we don't want things to move and so on, we've traditionally written this equation not as force, summation of the forces equals mass times acceleration, but we tend to write it like this. Summation of the forces minus the mass times acceleration equal to 0, which is obviously the same thing, right? Putting back my y here. So again, equals sum of the forces equals mass times acceleration, or sum of the forces minus the mass times acceleration equal to 0. In this sense, we look at the equation of dynamics as if it was an equivalent equation in statics. So what happens then is that we draw the inertial force, right? This is the inertial force, in a direction that is opposite to the positive acceleration. And so in this case, since y is positive to the right, we would say the acceleration is positive to the right, and so we would put an acceleration to the left and say there is an inertial load, which is mass times the second derivative of y with respect to time, right? And then we can treat this free body diagram as being a statical problem or an equilibrium problem. So from that sketch, let me raise the top here to give me a little room. So from that sketch, we can see then that summing forces in this direction, let's say, we would say that mass times acceleration, the double dots mean derivatives with respect to time, plus the stiffness coefficient of the spring times the displacement minus PT, or putting the PT in the other side, is this, right? So in this case, we can no longer say that the y is just P over K, because we have the inertial term. So this, the static problem is what? Is the problem in which this term is, the inertial term, is so small compared to the other term that we just simply discarded, right? Now, in this particular case, I place no energy dissipation. This would be a conservative system, you know. In any case, this problem, like this, is simply what? A second order differential equation. So given P as a function of time, this doesn't require any real engineering per se. I mean, you can give this to somebody that just knows a little bit of mathematics of differential equations, and if P is sufficiently simple, we can just solve for y as a function of time, right? And so on. Now, we will come back to this, of course, later on. But at this point, what I want to say is it's not to focus on the solution of this equation, but to focus on the next line here on the discussion, which says partial differential equations. So I'm going to erase the first term and assume that we already, you know, made sufficient observations. So I'll wrap it up by saying this. There are problems in which the load may be varying with time, but there is no need to do dynamics, because what we've got is just a sequence of statics problems, because the mass or the inertial forces that are associated in the solution to the problem are not relevant compared to the stiffness resistance to the applied load. That simply means that the load is applied too slowly in relation to the ability of the structure to react. If the structure can react very fast, for example, let's say if you consider, just as a last thing, imagine that you have, I don't know, a container like this sitting on the ground, let's say a box, I don't know, and this box, it's it's 1 foot thick, made of steel or something, and it's, I don't know, 10 feet high or something, and then what you have is a load here, P, which is applied, which is a function of time, but it's varying like this, where, I don't know, let's say that this is, I don't know, 2 minutes. So more or less in that scale, you can see that this load is varying so slowly that, well, I mean, here you could see perhaps a little bit of dynamics, because if it's going up fast enough, but you see my point. My point is that this structure, it's gonna, if you actually plotted how much this point will move due to this load, to any scale, it would look just like this plot also, right? There's no inertia, just the load. Even though it's a function of time, there's no dynamics here. Okay, so let's leave that aside then, and move on. So our next in line here is to point out that when we draw a mass, like in the previous example, and we say this is a point mass, this is an idealization, right? There are no point masses. Mass is always distributed. The problem is always one in which there is stiffness everywhere and there's mass everywhere. So what happens then is that we get not ordinary differential equations, but we get partial differential equations in dynamics. So the true solution of any problem in structural dynamics, if we really want to be precise, would have to be partial differential equations. Although we will in practice seldom deal with the question of partial differential equations, because it is significantly simpler to make approximations that allow us to use ordinary differential equations. But leaving that for next, let's consider for a moment, or for the next section of the discussion, the case of a rod. Let's say that this rod is of length L, that it has an area, let's say that it has an area equal to A, and that it has a modulus of elasticity equal to E, and that length is L. And let's say that at the end of this rod we have an applied load P of T. Okay, let's assume that the X, or not assume, let's postulate that the X-axis is running with the rod. Okay, excuse me for a second, let me click here just to make sure I keep my notation the same as I'm going to give you in a set of notes. Okay, so to be consistent with what the notes are going to show, I'm going to call the movement of points in the rod in the X direction, I'm going to call them mu, due to the load PT. Okay, and that's basically it. So we want to examine this situation. So for this purposes, let's say that we take a piece of rod which is of length dx, and we look at the free body diagram of it. So this is a dx section of the rod, and we would have a following situation. I'm assuming that the load is of course centrally applied and that the material is responding such that we have a uniform stress field here, just pure axial stresses. This stress is sigma that we have on this back side of the cut would be a function of x and a function of time, right? Now on the front side of this free body diagram, we can say that we have the stress is sigma that we had in the back plus how fast are the stresses changing in x. So we would say partial derivative of the stresses with respect to what? With respect to x, right? Multiplied times dx. So that would be the stress field over here, right? Now, those are those two stresses. What else is there? Well, it looks like there should be an inertial force, right? So this is a very thin slice. It's only dx. So since I'm taking accelerations to the right as positive, using again our technique of writing the thing as equilibrium, there will be an inertial force here, which would be the mass of that slither times the acceleration of this point. Now, how much mass? I should say, let's say that the density of the material, mass density, let's say it's rho. Okay? That is how much mass per unit volume. So we can say that the mass of this sliver here is going to be the density times the volume of this thing, and the volume of that is the area times dx, right? So that's the mass, and then that mass has to be multiplied times the acceleration of that slither, and the acceleration of that is, by definition, the second derivative of the displacement u, right? But in this case, with respect to time. So that, I believe, is the complete free body diagram, except I have to convert these stresses to forces, so before I sum, but basically that's complete because we're not considering any energy dissipation, right? So I will now erase so that we get some room to work on the top. And so I'll erase this. All right? And from this free body diagram, I will say sum of the forces in the x direction equal to 0. And I will have sigma, and I'm going to leave the x and t out to simplify the notation. It's clear that that's what I mean, right? So sigma plus the partial derivative of sigma with respect to x times dx multiplied times the area. That's a force going to the right, minus a force coming to the left, which is the same, force coming to the left is just sigma times the area. There is no partial here, right? And also to the left is the inertia, and so we have minus rho times the area times the second partial derivative of the displacement with respect to time times dx, right? Times dx. I believe that's everything, right? Make sure I get this thing correct. No, I didn't. Yes, I did. Rho a dx times the second partial of u with respect to time. And all of that must be 0, right? Okay, now I erase this. Hopefully I didn't leave anything out. And then we simplify. Now it's clear that this term, sigma a, will cancel with this sigma a, right? And that we're left with partial of sigma with respect to x dx times the area minus rho times the area times dx times the second partial of u with respect to time is equal to 0, right? All right, so we continue to simplify. We see that the area can be cancelled. Okay, we also see that the dx can be cancelled, and that we are left with the partial of sigma with respect to x minus rho times the second derivative of u with respect to time squared is equal to 0. Okay? Now, let me check here if I'm still doing all right, and I guess we are. I'm still maintaining the notation here. Okay, so now the next thing we're going to do, again, is give ourselves a little room. So we erase here. All right, and we continue by saying, okay, so this is a statement of equilibrium right here. Let's now assume that the material is linearly elastic, so that we can say that the stress is equal to the simplest expression of Hooke's law, which is the modulus of elasticity times the strain, right? Now, the strain as a function of the displacement is what in this problem? Is the partial derivative of the displacement with respect to the coordinate x, right? So we know that sigma is E times the partial of u with respect to x. And it thus follows from here that the partial of the stress with respect to x is just simply the derivative of this, which is equal to E times the second partial of u with respect to x squared, right? And so we have that. Therefore, substituting this here, we would get E multiplied times the second partial of u with respect to x squared minus rho times the second partial of u with respect to time is equal to 0. And I think at this point, I can take this out. I can take this out. And this is where we are, right? Now, dividing by E, we can write that the second partial of u with respect to x, two derivatives, minus E over rho, rho over E, minus rho over E, right? Times the second partial of u with respect to t squared is equal to 0. So you see that we've arrived at not at an ordinary differential equation, but at a partial differential equation, because we have derivatives with respect to x and derivatives with respect to time in the displacement field, right? We also see that the problem is governed not by the density of or by the modulus independently, but that the response depends on the ratio of the density by the modulus of elasticity. Now, let me see how far I want to take this by looking at the notes here. Well, so let's say, for example, that we wish to solve this thing. Of course, this doesn't even have anything to do with the loads at this point. So you could, let's say, for a little bit of an exercise, could look at the boundary conditions, right? And what are the boundary conditions of this problem? Well, I remind us that our rod looked like this, right? Our rod looked like this. So one thing we can say is that u at x equal to 0 for all time is equal to 0, right? That we know. So that's one of the boundary conditions that we have in this problem. the other thing that we know is a boundary condition associated with the presence of the load here at the tip, which means that the stress at the tip, right? So sigma at x equal to L for all time is equal to PT divided by A, right? Because over there, that's just the edge, and at the edge, at least under idealized situation, right? You might say, in reality, if this is a concentrated load, then of course that's not true because there's an edge effect and so on. But this is not what we're considering. We're considering the idealized case in which that load PT, if you like, is not really applied like that. It's, to be really precise, I should say that that load is the resultant of a stress field which is applied already uniform at the end. So what we are really applying is PT over A, and this is the result. Okay? Now, sigma that we have is equal to what? Sigma was equal to E multiplied times the first derivative of U with respect to X, right? So what we're saying is that that evaluated at X equal to L for all T must be equal to PT divided by A, and therefore we can also say, running out of room here, but try to put it here on the top, we can say that the partial derivative of U with respect to X evaluated at X equal to L for all time must be equal to PT divided by A divided by E, right? And okay, and we get to that point. Now, we could try to solve the problem even further, and in fact, I have a handout that I will decide a little bit later whether we want to do it or not, you know, to delve into it, because there's quite a few interesting things that one can do by continuing along these lines. But I think at this point, for the purposes of this introductory lecture, it's sufficient to simply point out or emphasize that if you consider a problem and you account for the distributed nature of the mass, right, what you end up whenever you formulate a dynamic problem is not going to be something like mass times the derivative of the displacement, but you're going to find a partial differential equation-ish, okay? And that brings us to the fact of, well, that brings us to the next line, because that means I can erase these partial differential equations, and it takes me to this thing that says DOF. Because DOF, by DOF we mean degrees of freedom. So let me discuss then the issue of degrees of freedom, the all-important issue of degrees of freedom from the point of view of clear understanding. So if we wanted to do the rod exactly, we would have to solve this equation. Well, let's say that we don't like this equation because this equation is not, you know, it's not algebra. I cannot really program it and solve it by taking it, well, you know, I'd have to solve the equation with its boundary conditions and so on. That may be hard. Now, it's clear that I can convert this problem into a problem that is not a partial differential equation problem, but one of ordinary differential equations by, for example, dividing the rod in pieces and assuming that what I have really is a set of springs with little masses connected to each other, right? So let's say that what I've done, maybe I can erase this, what I can do is to say that the actual rod is not equal, but it's approximately, back, wait. It's approximately equal, right, to this. Now, of course, we're talking only in the horizontal direction. If you said, in this particular case, it suffices to know how much each one of these masses are moving, because given the movement of these masses, we can calculate the force in the springs and so on. And we would refer to this problem as having 1, 2, 3, 4, 5, 6 degrees of freedom, or coordinates that we need to describe the problem. Now notice, and this is the point I want to make, that this 6 degrees of freedom is not an innate property of this rod. This is actually a decision that I've made as a user on describing the structure with a finite number of degrees of freedom. The actual rod has infinite degrees of freedom, and I may make a model. So models have degrees of freedom, real structures don't, because real structures have infinite. They have distributed mass and so on, right? So models have degrees of freedom, and the degrees of freedom in the model, sometimes we forget because we get into this habit of always saying, oh, a frame has this many and so on, but there's a lot of implicit assumptions that have already been accepted when we use that language. In this particular case, it's obvious. I can make a model of this rod with 6 degrees of freedom. I could make it with 60 degrees of freedom. I could make it with 600 degrees of freedom, and so on, right? As the number of degrees of freedom that I put, or the number of masses that I use, gets increased in this case, the actual model that uses low masses approaches the real rod further and further, right? Now, so the first point is that degrees of freedom is a property of the model, not of the structure that we've made. Let's see, what else it's important to say. Let's say that we take a look at this one, 1, 2, 3, 4, 5, 6, that we take a look at that one, and you know, if you want, you can map the locations of these masses, if you'd like, to the actual physical locations in the rod, right, something like that. I don't pretend to be precise here as to, you know, maybe you should have put this one here or there. That's not important for what I'm talking about. Now, let's say here that we found, let's say that we call this number 1, number 2, number 3, number 4, number 5, and number 6. And that at a given time, t equal to t1 or ta, we said that u was equal to A1, A2, up to A6, 6 numbers, right? Whatever they were. That's fine. Now, if I asked you, what is the displacement, what is your estimate of the displacement in the rod in the very middle between 4 and 5 at this time? What is u here at t equal to ta? Right? I think most of you would say, well, it's not in the model, but I would take it as the average of 4 and 5 or something like that, right? And that's totally reasonable. But the point I want to make is that when we assign to a structure a set of degrees of freedom, implicitly often, sometimes explicitly, but certainly many times implicitly, we've actually assumed the displacement field in between the coordinates. Okay? That is, for example, here you might have assumed, even though without saying it, that the displacement field between points where you are giving it values, it's linear. Okay? Because of course the domain is continuous. So the fact that we only have values at a certain number of points doesn't mean that suddenly we know nothing of what happens in the middle. Well, what happens in the middle has been pre-decided, okay? And so you could say that what we've done, what the degrees of freedom do, is they become the scalars of of patterns. Let me explain again. This is important to emphasize, to try to be clear. So let's say I have this beam, this simple beam. Okay, simply supported beam. And that this simply supported beam has a distributed mass m per unit length, and the beam is of length L. Okay? Now, how many degrees of freedom does this beam have? Infinite. Like every structure. If I want to really be precise, I'm going to get partial differential equations. Now, let's say that the boss at the company says that you want to make a model with 3 degrees of freedom of this beam for some dynamic analysis about impact of a big weight that's going to fall on the beam, whatever. So let's say that you say, okay, I've been told to make a 3 degree of freedom model. So, I haven't really done very much with this, but my intuition tells me that I should be able to get something reasonable if I do something like this. So I take one mass here, one mass here, one mass here, right? And I say, well, I'm going to assume now that the beam has no mass, right? So I'm going to replace, actually let me do this again. Where is the eraser? Excuse me. Oh, it's in the floor. Yeah, instead of drawing it here, let me just leave the real beam alone, and let me say that what I'm going to do, I can't draw this approximately equal sign. What I'm going to do is to say I'm going to replace the beam, the real beam, by this, where this is massless, right? And these are, I don't know, something reasonable, the mass from here to here, etc. And then I'm going to say that my concern is only the movement of this point, the movement of this point, and the movement of this point, and I hope to perform or arrive at the equations of motion and do the dynamics on what will eventually be a 3 degree of freedom problem. We don't have to get into the specifics. The point is that this would have 3 degrees of freedom. Now, here comes the question that is less obvious than before. If I told you that at some time t equal to ta, you had y1 equals to 3, and it just so happened that y2 was 0 and y3 was 0. What would you say it's happening between y2 and y3? To the displacement field at that time. What do you think is happening between y2 and y3? In this case, I don't know if, some people might say, well, I don't know, I'll take it as 0 or something like that. But you might actually do and say, no, I'm going to assume the following. I'm going to assume that if y1 has a value and y2 doesn't and y3 doesn't, that what I'm really assuming is that my beam would look like that, because I have to have continuity and so on. So this looks like a better guess to me. And what would that shape be? Well, that might be the shape that I'll get if I move this point statically and hold this in place and so on. Okay? Now, following that line, you could also say, well, what happens if instead of y1 having some value, and these other ones don't have any value, I had values in y2, but none in y1 and not in y3? Well, then it might be also along the same lines, you might be thinking that this is not so bad, right? To assume in this case, this is y1 not equal to 0, this is y2 not equal to 0, right? And you could say, well, okay, well, what about, let's complete it with y3 not equal to 0. which would look just like y1 but on the other side, right? So now y3 is not equal to 0, but y2 and y1 are 0, and we get something, let's say, like this, right? So in this particular case, we can see that the degrees of freedom y1, y2, y3, which are movements of the masses, I could also think in terms of the degrees of freedom not being the movement of the masses. I could think in terms of the degrees of freedom as being the amplitudes of these shapes. So I could say this shape multiplied by alpha 1, which is a function of time. This shape multiplied by alpha 2, which is a function of time. And this shape multiplied by alpha 3, which is a function of time, is the deflection of the beam at any time. So the degrees of freedom, sometimes we think about them as being physical, visualizable movements, or rotations or something. Sometimes we think about them as being shapes multiplied by amplitudes. And in most texts, these things are presented as if they were completely different. In my mind, they're the same thing. You always have an assumed shape, okay? You always have an assumed shape, because the domain has to be interpolatable when the degrees of freedom are known. So you can think about this problem as having y1, y2, y3, or you can think about this problem as having alpha 1, alpha 2, and alpha 3, and these are the shapes. You get to exactly the same thing, okay? Now, a last word also with degrees of freedom. And let me be conventional here a little bit. If we were to look at this problem, and since we are, I think most of us are in structures, although this doesn't really have to be only understood by people in structures, but let's say you consider a system like that, okay? And let me give it some width. This is not working so well, but give it some width here, okay? Let's assume that this structure is excited by some dynamic load, P of t, which is applied there, so that it starts moving to the side like this, right? Back and forth. Well, it turns out that most of the inertia is going to be associated with the floors, because this level contains, remember this is 3D, right? So there's going to be another one behind, and so on. So most of the mass of this structure is going to be contained here. So for the purpose of dynamics, the only inertia that matters is really the horizontal inertia of this level. So from that point of view, you would say that this system could be analyzed probably using only 1 degree of freedom, because there's only one inertia. As long as I know what is the time history of this horizontal movement, I can probably do what I want, okay? And we don't have to know the specifics, except that it looks like, you know, whatever the weight of these columns is, I can add them to the floor and then take half of the way down to the ground, and that's it, right? What I really need is to know what is the horizontal motion of that mass. So, seems like 1 degree of freedom would be sufficient for my dynamics problem. But if I look at this structure, and the problem was not in a class of structural dynamics, but the problem was in a class of structural analysis, traditional, then people would tend to say, okay, well, this structure has how many degrees of freedom from the point of view of a conventional analysis? Well, most people would say it's got 6, because this is what a computer program that uses the stiffness method would actually assign to this thing. 1, 2, 3, let's say 4, 5, and 6, right? So for a static analysis, this problem would be assigned 6 degrees of freedom. However, for dynamic analysis, we would say that we would have 1. The process of reducing the degrees of freedom to the degrees of freedom of a dynamic analysis, it's one that it's important to understand and be clear on. Some of them are assumptions and some of them are condensations due to the fact that there is no inertia. For example, in this particular case, essentially what we would say is that degrees of freedom, this is not so clear, but degrees of freedom 2 and 6 are essentially 0. That is, there's going to be essentially no vertical motions, so compared to the horizontal sway, so we get rid of those. The other thing is, we say this bar doesn't elongate hardly, so we would say that degree of freedom 1 is equal to degree of freedom 4, and so we essentially can say, let's get rid of this 4, 1 is really throughout, right? So it's the same, 1 and 4 are the same, so just the horizontal motion of this level, right, is degree of freedom 1. Now we got 3 and 5 left. Now 3 and 5 are not necessarily very small. We don't want to say that they are 0, because if we say they are 0, these joints can rotate. But what we're saying is that 3 and 5, okay, are what? Are not dynamic degrees of freedom. That is, they are not associated with inertia themselves. So then we say that this degree of freedom, which is the one that is associated with inertia, is the master. That these degrees of freedom, which are not associated with inertia, are slaves. And even though I don't have to do it at this moment, or I will not do it at this moment, but, well, I don't know, maybe I will. What we're saying is that degrees of freedom, and the name masters and slaves is because degree of freedom 3 and 5 are determined by degree of freedom 1. In other words, if I know degree of freedom 1, I know where 3 and 5 are, because I am forcing my structure to behave in a way. I wish I had another, this markers. Let me see if I have other markers here. Wait a second. Nope. No more markers here. Okay, maybe I'll have to stop the thing if they get worse and go look for some more. But what we say is that degree of freedom 3 and 5 would have to follow number 1. That is, for example, we would say if degree of freedom 1 is here, that means that the structure has no choice but to look like this, and so the rotation of this joint and the rotation of this joint which is 3, theta 3, theta 5, are a function of delta 1. Okay? So, okay, so in summary, we may have a large set of degrees of freedom in the description of a finite element model. So we may have a very large number of degrees of freedom. Now, but we're going to do a dynamic analysis. That does not mean that all these degrees of freedom are dynamic. Okay? Some of them, for the purposes of reducing the size of the problem, we may take them as 0. And many of them, which are not associated with significant inertias, are what we refer to, we are condensed. That is, they are taken out of the problem by expressing them as a function of the others. Now, let me see. I'll indulge mathematically for a second here as follows. Imagine that our problem that has mass and stiffness can be written like this. Mass of the P, mass of the S's, 0, and 0, so that the mass matrix is the mass of the system, the description. I know we haven't talked about matrices, but I think it's not that hard to follow. This can be written like this. Let's say that the degrees of, oh, okay, here I'm being more precise. Let's say that the degrees of freedom, are partitioned into P and S. And at this point are not, I do not specify what P and S are, it's just an arbitrary partition. So now the stiffness matrix then becomes KPP, KPS, KSP, and KSS. And that partition matrix multiplied times YP and YS. And then there is something on this side, which is the loads at the P's and the loads at the S's, let's say. Okay, I'm not putting any damping, but keeping it like that. Now, these are degrees of freedom, just partitions into P and S's, right? In a static, the degrees of freedom were decided on the basis of conventional static procedures. Now I want to make the problem smaller because for dynamic analysis it's a lot of effort and so on. So I'm going to say, okay, you know what, when I partition these degrees of freedom into P and S, I really took the S's so that they have really very small mass. So now that means that I'm going to approximate this problem by saying, oh, this is the good one, by saying, I'm going to say this is MP and these guys are 0, okay? So there's no inertia associated with these degrees of freedom. So we have Y double P and Y double S, right? Plus, and then we have this, KPP, KPS, KSP, KSS, YP, YS. Now, I don't have to do this, it's not necessary, but since this is an introductory lecture, I'm going to keep it as simple as possible. So I'm going to say, let me assume also that the S coordinates are really not loaded. They could be, and it doesn't change the thing, but this will be easier. And it doesn't really affect the main point. So let's say that I am going to say that these coordinates are not loaded. So you can see that if you do that, the second partitions of these equations read 0 times this, right? It reads like this, KSP times YP plus KSS times YS is equal to 0, right? These are functions of time. I mean, the YP and the YS. So, voila, that's what we wanted to. It says that YS is equal to minus the inverse of the SS partition multiplied times the KSP partition multiplied times the YP partition, right? Which tells me what? The slaves are determined by the primaries or the masters, okay? Now, if that is true, that I am accepting that approximation, then I can come to the first set of equations and write MP times Y double dot, that is the second derivative of the primaries, plus KP P multiplied times YP plus KPS multiplied by YS. But instead of YS, I'll just write this, right? Which is minus KSS to the minus 1 KSP times YP. And then all of that is equal to PPT. And we then see that this is simply MP YP double dot plus parentheses KPP minus KPS KSS to the minus 1 KSP times YP is equal to PPT, right? And we have achieved the typical equation, right, that we expected and that we have from the single degree of freedom looking the same, right? Which is some masses times accelerations. This one here is just another stiffness. We can call it K condensed times YP is equal to PPT. And so this is the equation that maybe I want to solve in dynamics. And my original degrees of freedom, maybe I had, 50 P's and 300 S's. So what I'm solving is really this 50 degree of freedom problem here, not the 350 big one, right? The stiffness of the problem depends on this part, and there are more details, but the point is, and I'll close it with this simply, that we have a set of degrees of freedom in the finite element model that we can normally divide into those that have significant inertia and those that do not have significant inertia. When I say they have, I mean their value doesn't induce significant inertia into the system. If that is true, it is often convenient, in order to reduce the size of the problem, to condense out of the dynamic formulation these degrees of freedom. Okay? So we take out the degrees of freedom that do not have significant inertia. Okay. So that takes out this part here, degrees of freedom. And I'm going to stop for a second just to check out that the recording is going fine.